You are not dreaming of a world, you know. The place you have come to, the place you are drifting through right now, has no cities glowing on the dark side of a planet, no campfires burning at the edge of a forest, no sun rising gold and slow above a hill. There is none of that here. There is no hill. There is no forest. There is no sun. What stretches around you in every direction is something your waking mind has no name for, because nothing in the life you have lived has ever prepared you for a darkness this complete, a silence this total, a stillness this absolute. And yet you are here. And somehow, impossibly, you are at peace. Let your body settle into wherever you are resting. Let the weight of the day, the small worries, the unfinished conversations, the lists you have been carrying, begin to soften at the edges. You do not need them here. They belong to a world that is very far away, a world full of light and noise and urgency. That world is behind you now. The world ahead of you, the one you are floating into, is something else entirely. It is older than you can hold in your mind. It is quieter than anything you have ever heard. It is, in its own way, beautiful. This is the universe after everything. Try to imagine, not with effort, but with the gentle curiosity of someone half asleep, what it would mean for the stars to be gone. Not just the stars you can see from a dark field on a clear night, though those are already gone. Not just the billions of stars in the galaxy you once called home, though those are gone too. Every star that ever burned in every galaxy that ever formed, every one of them, from the smallest red dwarfs that glowed like embers for trillions upon trillions of years, to the great blue giants that blazed and died in a cosmic breath. All of them have run through their fuel, collapsed, and gone cold. The sky is no longer scattered with light. The sky simply is, vast and dark and patient, curving around a universe that has grown very, very old. You float in that sky now, and there is no up, no down, no horizon. Just depth. Depth in every direction, folding into more depth, and somewhere far below the threshold of your perception, the faintest whisper of heat, the last remnant of an era when things burned. That era is over. The story of how the universe arrived at this moment is a story told in 3 long, slow chapters, and you have slept through most of it. You were not there for the beginning, the brilliant first instant, when everything that would ever exist exploded outward from a point smaller than a thought, when light and heat were indistinguishable from each other and time itself was something new and uncertain. You were not there for the middle, the long luminous era, when hydrogen collapsed into stars and stars forged heavier elements, and those elements were flung across space to become planets, oceans, the soft tissue of living things. You were not there for that either. But you are here for the ending. The first chapter was fire, nuclei forming, atoms cooling, matter pulling itself into clumps and sheets and filaments, galaxies assembling like slow storms, stars igniting by the billions. For billions of years the universe was a place of almost incomprehensible brilliance, light traveling in every direction at once, new suns being born even as old ones died. It was never quiet. It was never still. It was a place of constant becoming. Then slowly, the rate of star formation began to slow. Galaxies used up their reservoirs of gas. The great molecular clouds that had been nurseries for new stars gradually emptied. Stars still burned, but fewer new ones were being born to replace them, and the ones that remained burned through their fuel at their own unhurried pace, some lasting billions of years, some tens of billions. The universe was still bright, but the brightness was no longer growing. It was beginning, very quietly, very gradually, to fade. That was the second chapter, the long fading. And then came the third. The last stars to burn were the smallest, tiny red dwarf stars, miserly with their fuel, hoarding it over timescales that make the current age of the universe look like an afternoon. Where a star like your old sun might burn for 10 billion years, a red dwarf might burn for 10 trillion, or 100 trillion, or longer still. They glowed dimly, reddish and cool, scattered across a darkening universe like coals left after a fire has mostly died. For a long time, longer than you can hold in your mind without letting it dissolve at the edges. Those small stars were the only light left. And then they too went out. One by one, over periods of time so vast they fold back on themselves, the last red dwarfs exhausted what little fuel they had. They did not explode. They did not burn dramatically. They simply stopped, each one cooling through a long, slow gradient, red to infrared to the dull warmth of a dying ember, until they were no longer stars at all, but cold, dense spheres drifting silently through the dark. White dwarfs cooling toward black. Neutron stars spinning slowly in the silence. The wreckage of stellar evolution, scattered across a universe that had forgotten what light was for. The universe entered what some have called the Dark Era. And what remained in that darkness were the black holes. Breathe in slowly. You do not need to understand any of this fully. Understanding is not what you came here for. You came here to rest, to let the immensity of these scales wash over you the way deep water washes over stone. Not breaking you, not overwhelming you, just pressing gently, insistently, until the small tensions in your body begin to loosen, until the muscles in your shoulders soften, until the thoughts that cling to the surface of your mind begin to drift away like leaves on a very slow river. You are floating in the universe after everything. Around you, in every direction, there is almost nothing. No light, no stars, no the warm haze of a galaxy seen edge-on across millions of light years. The structures that once organized matter into something recognizable, the filaments, the clusters, the great walls of galaxies, have long since dispersed. The expansion of space has pulled everything apart, stretched the distances between remnants until even the word between feels inadequate, feels too human and too small for what separates things here. But there are black holes. Not many, by the standards of the luminous era. But they are here, drifting through the dark, invisible and immense, the final inheritors of all that mass, all that matter, all that was once stars and gas and the long, bright architecture of galaxies. They do not shine. They do not announce themselves. They simply exist, with a patience and a certainty that nothing else in this universe can match. They are the last major objects. They are, for now, everything. Let your eyes close a little more, if they are not already closed. Let the darkness behind them feel less like the absence of something and more like a presence, a vast, unhurried, encompassing presence that has been here long before you arrived and will be here long after you have drifted off into sleep. The universe has been building toward this moment for longer than numbers can comfortably describe. 14 billion years to produce you, to produce the particular arrangement of atoms and electricity and memory that is you reading or hearing these words. And then trillions of years beyond that, the slow unwinding of the stellar era. And then quadrillions more, the fading of the last dwarfs. And all of that unimaginable accumulation of time, has led to this, a universe that is dark and quiet and dominated by black holes. They are the endpoints of gravitational collapse. When enough mass gathers in a small enough space, space itself curves inward, curves so sharply that even light, even the fastest thing there is, cannot escape. A black hole is not quite a thing and not quite a place. It is more like a condition, a permanent arrangement of space-time around a point of infinite density, a place where the ordinary rules of the universe reach their limit and curl under and stop making sense. It is the universe's way of saying, here, nothing more can happen. Here is where the story ends, for this particular piece of matter. And yet the black holes are still here, still waiting, because even for them, the story is not quite over. There is something that will happen to them, something that takes so long to happen that even the dark era, even those unthinkable trillions of years of silence, is only the beginning of the wait. Something discovered in theory, whispered about in equations, that says, slowly, imperceptibly, over timescales that dwarf everything that has come before, black holes evaporate. They do not explode. They do not collapse further. They leak. Very, very slowly, they give back to the universe a faint trickle of radiation. Energy so diffuse and so cold it is barely distinguishable from nothing at all, and in doing so, they lose mass. A little at a time. An unimaginably little at a time. Over periods so long they require new words, new notation, new ways of holding numbers in the mind. But you do not need to think about that yet. For now, just float here, in this universe after everything, in this dark and patient sea. The black holes are around you. You cannot see them, but you can feel or imagine feeling their presence, the way you sometimes sense the presence of something large and quiet nearby, even in total darkness. A gravity of attention, a depth that pulls you gently inward, not into fear, but into rest. The universe is very old here, and it is very calm, and so slowly are you. Let your breath find its own rhythm. Let your thoughts thin out, like the last faint wisps of gas between the stars, or where the stars used to be. Let the distances carry you. You are safe here in this long dark, this beautiful and melancholy aftermath. There is nothing left to hurry for. Sleep if you are ready, or simply drift and let the dark hold you, while the last black holes wait in the silence, patient beyond all measure, for whatever comes next. You are still here. The darkness has not changed. It is still the same immense, unhurried dark that held you at the end of the last drift, but something in you has shifted very slightly. The way the body shifts in the first hours of deep rest, settling a little further into itself, releasing something it had been holding without knowing it was holding it. You are heavier now, in the good way. Heavier and slower and more at ease. The thoughts that were moving through you have grown quieter, more widely spaced, like stars spreading apart as a galaxy stretches and thins. Let that feeling continue. Let it deepen. You are floating in the universe of the far future, in the era that comes after stars, after galaxies, after all the brilliant, turbulent machinery of the luminous age. The light is gone. The noise is gone. And what remains, what surrounds you in every direction, invisible and vast and certain, is the era that astronomers, thinking carefully about the very long arc of time, have come to call the black hole era. It is not a dramatic name. It does not promise explosions or collisions or the blazing spectacle of stellar birth. It promises something quieter than that, something darker, something that, once you let your mind settle into it, turns out to be unexpectedly peaceful. This is the age of the last great structures. This is the age of the black holes. To understand what it means for black holes to inherit the universe, it helps to remember gently, without effort, what came before. There was a time, long ago in the deep past of this cosmos, when matter was restless. Hydrogen clouds collapsed under their own gravity. Cores ignited. Fusion began, the slow, sustained burning of lighter elements into heavier ones, a process that released energy as light, as heat, as the slow radiation that warmed the surfaces of planets and drove the chemistry of living things. Stars were, in a sense, the universe's way of doing work, of releasing the potential stored in matter since the first moments after the beginning. And for billions of years, that work continued. New stars formed from the ashes of old ones. Supernovae scattered iron and carbon and oxygen across interstellar space. Galaxies turned, slow as wheels, lit from within by the accumulated light of hundreds of billions of suns. The universe was bright and busy and full of the particular kind of complexity that arises when energy flows freely and matter has somewhere interesting to go. But all of that required fuel, and fuel runs out. The great reservoirs of gas that fed star formation gradually emptied. The rate of new stellar birth declined, slowly at first and then more steeply, until the galaxies began to look more like museums than nurseries, full of old stars finishing long lives, with fewer and fewer young ones to replace them. And one by one, over timescales that make the current age of the universe feel brief and recent, those old stars reached the ends of their stories. Some ended quietly, collapsing into white dwarfs that cooled over trillions of years into cold, dark spheres. Some ended more dramatically, in the collapse of massive cores into neutron stars, spinning and dense beyond easy comprehension. And some, the most massive, the ones with the most to give and the most to lose, ended in the only way available to them. They fell inward so completely, so absolutely, that they became black holes. Places where gravity had won every argument, permanently and without appeal. And those black holes endured. There is something worth sitting with here in the dark. The idea that the universe has a shape, not a spatial shape, not a sphere or a saddle or a flat plane, but a shape in time, a trajectory, a long, slow arc from the chaos of the beginning through the luminous middle and into this, the quiet end. And at every stage of that arc, the universe has been dominated by whatever structure was most stable, most enduring, most resistant to the forces pulling everything toward dissolution. In the early universe, it was radiation, pure energy, too hot for matter to organize itself. Then it was atoms, clouds of hydrogen and helium assembling under gravity. Then stars and galaxies, the great organizing structures of the luminous era. And now, here in the far future, after everything else has run its course, it is the black holes. They are the most stable things the universe ever made. Not in the sense that they are unchanging, we will come to that, in time, but in the sense that nothing in the ordinary laws of physics can destroy them quickly. They do not burn out. They do not explode under their own weight. They do not radiate their mass away on any timescale that feels meaningful relative to what surrounds you now. They simply persist, heavy and dark and present, holding the mass that was once stars and gas and the bones of galaxies, holding it in a form from which there is, for now, no escape. They are the final islands of structure in a sea that has become almost perfectly empty. Let your body sink a little further into rest. You do not need to hold any of these numbers in your working mind. They will drift through you like the dark drifts through the space between remnants, present, pervasive, but not demanding anything of you. Just let them pass. Just let the scale of things move through you without snagging, the way deep water moves through the gaps in something that was once solid. The universe around you is vast in a way that has no useful comparison. The distances between things, between these last gravitational islands, these surviving black holes, are not distances you can walk or fly or even meaningfully imagine. They are distances that would take light millions or billions of years to cross, and there is almost nothing along the way. No dust, no gas, no faint background of microwave radiation that once spoke of the early universe's heat, because even that has redshifted into something too cold to measure. Just space. Space and time, continuing to expand, continuing to thin, continuing to spread whatever remains ever further apart. And in that space, patient, unhurried, anchored by gravity alone, the black holes drift. Not all of them are the same. In the luminous era, black holes came in a wide range of masses. Some formed from the collapse of individual massive stars. These were relatively small by black hole standards, a few times the mass of a sun, maybe 20 or 30. Stellar mass black holes, physicists called them, born in the depths of the heaviest stars. They are here in the darkness, these smaller ones, drifting through the emptiness like cold stones dropped in a still pond, sending no ripple outward, making no announcement of their presence. But there were others much larger. At the center of almost every galaxy that ever formed, there lurked what astronomers came to call a supermassive black hole, an object so far beyond the scale of stellar collapse that its origin is still a question with several possible answers, none of them simple. These central black holes grew over billions of years, fed by the gas and stars that fell toward the gravitational center of their host galaxies, swelling in mass until they reached millions, hundreds of millions, sometimes billions of times the mass of a sun. The one at the center of the Milky Way, your old galaxy, if you will forgive the possessive, was modest by these standards. Several million solar masses. A quiet giant, not actively feeding by the time the stellar era ended, just sitting at the galaxy's heart as the stars around it slowly cooled and faded. Others were far larger. The black holes at the centers of the largest galaxies grew to extraordinary sizes, fed during the brilliant quasar era by torrents of infalling gas, glowing so brightly they could be seen across billions of light years. Those periods of feeding eventually ended. The quasars went dark. The supermassive black holes settled into silence. But they kept the mass they had gathered. Every solar mass of gas that ever spiraled into them, every star torn apart by tidal forces, every collision and merger with other black holes. All of it added to their final weight, and none of it could be taken back. Those are the giants of this era. The black holes at the centers of what were once the largest galaxies. Some of them carry the mass of tens of billions of suns, some even more. They are, in the long inventory of what the universe has made and kept, the heaviest things that exist, the most gravitationally dominant, the most enduring. They will be, when the final accounting is made, the last objects to survive. Breathe slowly. Imagine, not urgently, just as a soft image behind your eyes, what it would look like to watch this era from a great distance, with a kind of time-lapse vision that could compress trillions of years into a single long breath. You would see the galaxies fade, the last red dwarfs blinking out one by one across their host galaxies, the galaxy itself growing darker in patches, like a city at night losing power district by district, until finally the last light goes and the whole structure is dark. What remains of the galaxy is not nothing. It is a loose collection of cold remnants, white dwarfs gone black, neutron stars cooling, stellar mass black holes drifting on old orbits. But it no longer shines. It no longer has the shape that the word galaxy implies. And at its center, unchanged, is the supermassive black hole. It does not care what has happened to the stars around it. It does not register the loss. It holds its mass with the same indifferent certainty it always had, and it waits. The remnants around it, those dark stellar corpses, will eventually, over even longer timescales, scatter. Their orbits will decay by tiny amounts through gravitational interactions, through the emission of gravitational waves, through the slow diffusion of energy, through a system that no longer has the friction or the gas clouds to damp out the motion quickly. Some of them will be flung outward into intergalactic space. Some of them will fall inward, consumed by the central black hole, adding their mass to its already enormous total. Over immense timescales, the galaxy, what was left of it, will dissolve. The central black hole will remain. There is something quietly moving about this, if you let yourself feel it. These great black holes at the centers of galaxies were there almost from the beginning. They formed when the universe was young and hot and full of gas, when the first structures were still assembling themselves out of the primordial fog. They watched, if watched is the right word, if watching is something that can happen in the absence of perception, as the galaxies built themselves around them, star by star, cloud by cloud, collision by collision. They were present for the whole of the luminous era. For every star that formed and burned and died, for every planet that cooled and cracked and perhaps, in some places, for a while, held something alive. They were there for all of it. And now the living things are gone, and the stars are gone, and the galaxies are gone, and the black holes are still here. The last islands, the final structures, each one a kind of monument to everything that fell into it, everything that was consumed in the long history of its growth. All that gas, all those stars, all that matter that was once part of something else and is now folded into the deep gravity of this dark, patient, permanent thing. You are resting near one of them now. Not close enough for danger. There is no danger here, this is a dream of distance and time, but close enough to feel the weight of its presence, the way you might feel the presence of a mountain in the dark, not seeing it, but knowing it is there, knowing it changes the shape of the world just by existing. Let that weight settle over you like a blanket. The black hole era is long, longer than everything that came before it. The universe will spend more time in this dark, quiet, black hole-dominated age than it spent in all the stellar generations combined. And for almost all of that time, nothing will happen that you could call an event. No explosions, no births, no sudden illuminations. Just the slow drift of the last remnants through the expanding dark, and the black holes at the centers of what were once galaxies, holding their mass, holding their place, holding the memory of a universe that used to burn. They are everything now. They are for a long, long time, the longest time, all there is. Let yourself rest in that, as you rest and sleep. Let the scale of it carry you somewhere very quiet, somewhere underneath the noise of ordinary thought, where the distances are so vast they have become a kind of silence, and the silence has become a kind of comfort. The black holes are here. They will be here for a long time yet. And so for now, you are still floating. The dark is the same dark it has always been here, deep and even and without edges, and you are still moving through it at the pace of a dream, which is to say you are barely moving at all, drifting so slowly that the word drifting is almost too active, almost too purposeful for what this is. What this is rest. What this is the particular stillness that comes when the body has finally let go of the day and the mind has not yet found anything new to hold on to. Stay here a little longer. Others were far larger. The black holes at the centers of the largest galaxies grew to extraordinary sizes, fed during the brilliant quasar era by torrents of infalling gas, glowing so brightly they could be seen across billions of light years. Those periods of feeding eventually ended. The quasars went dark. The supermassive black holes settled into silence. But they kept the mass they had gathered. Every solar mass of gas that ever spiraled into them, every star torn apart by tidal forces, every collision and merger with other black holes, all of it added to their final weight, and none of it could be taken back. Those are the giants of this era. The black holes at the centers of what were once the largest galaxies. Some of them carry the mass of tens of billions of suns, some even more. They are, in the long inventory of what the universe has made and kept, the heaviest things that exist, the most gravitationally dominant, the most enduring. They will be, when the final accounting is made, the last objects to survive. Breathe slowly. Imagine, not urgently, just as a soft image behind your eyes, what it would look like to watch this era from a great distance, with a kind of time-lapse vision that could compress trillions of years into a single long breath. You would see the galaxies fade, the last red dwarfs blinking out one by one across their host galaxies, the galaxy itself growing darker in patches, like a city at night losing power district by district, until finally the last light goes and the whole structure is dark. What remains of the galaxy is not nothing. It is a loose collection of cold remnants, white dwarfs gone black, neutron stars cooling, stellar mass black holes drifting on old orbits. But it no longer shines. It no longer has the shape that the word galaxy implies. And at its center, unchanged, is the supermassive black hole. It does not care what has happened to the stars around it. It does not register the loss. It holds its mass with the same indifferent certainty it always had, and it waits. The remnants around it, those dark stellar corpses, will eventually, over even longer timescales, scatter. Their orbits will decay by tiny amounts through gravitational interactions, through the emission of gravitational waves, through the slow diffusion of energy, through a system that no longer has the friction or the gas clouds to damp out the motion quickly. Some of them will be flung outward into intergalactic space. Some of them will fall inward, consumed by the central black hole, adding their mass to its already enormous total. Over immense timescales, the galaxy, what was left of it, will dissolve. The central black hole will remain. There is something quietly moving about this, if you let yourself feel it. These great black holes at the centers of galaxies were there almost from the beginning. They formed when the universe was young and hot and full of gas, when the first structures were still assembling themselves out of the primordial fog. They watched, if watched is the right word, if watching is something that can happen in the absence of perception, as the galaxies built themselves around them, star by star, cloud by cloud, collision by collision. They were present for the whole of the luminous era. For every star that formed and burned and died, for every planet that cooled and cracked and perhaps, in some places, for a while, held something alive. They were there for all of it. And now the living things are gone, and the stars are gone, and the galaxies are gone, and the black holes are still here. The last islands, the final structures, each one a kind of monument to everything that fell into it, everything that was consumed in the long history of its growth. All that gas, all those stars, all that matter that was once part of something else and is now folded into the deep gravity of this dark, patient, permanent thing. You are resting near one of them now. Not close enough for danger. There is no danger here. This is a dream of distance and time, but close enough to feel the weight of its presence, the way you might feel the presence of a mountain in the dark, not seeing it, but knowing it is there, knowing it changes the shape of the world just by existing. Let that weight settle over you like a blanket. The black hole era is long, longer than everything that came before it. The universe will spend more time in this dark, quiet, black hole-dominated age than it spent in all the stellar generations combined. And for almost all of that time, nothing will happen that you could call an event. No explosions, no births, no sudden illuminations. Just the slow drift of the last remnants through the expanding dark, and the black holes at the centers of what were once galaxies, holding their mass, holding their place, holding the memory of a universe that used to burn. They are everything now. They are for a long, long time, the longest time, all there is. Let yourself rest in that, as you rest and sleep. Let the scale of it carry you somewhere very quiet, somewhere underneath the noise of ordinary thought, where the distances are so vast they have become a kind of silence, and the silence has become a kind of comfort. The black holes are here. They will be here for a long time yet. And so for now, will you? You are still floating. The dark is the same dark it has always been here, deep and even and without edges, and you are still moving through it at the pace of a dream, which is to say you are barely moving at all, drifting so slowly that the word drifting is almost too active, almost too purposeful for what this is. What this is rest. What this is the particular stillness that comes when the body has finally let go of the day and the mind has not yet found anything new to hold on to. Stay here a little longer. Not the darkness itself, not the absence of stars or galaxies or light. Those are conditions. What truly defines this age, what makes it something the mind has to approach sideways, gently, without expecting to fully grasp, is the time. The sheer, uncontainable, almost incomprehensible amount of time. Begin with something familiar. In a loose and comfortable way, that the universe is old. 14 billion years old, roughly. 14 billion years since the beginning, since the first fraction of a second, when everything was smaller than an atom and hotter than anything has been since. 14 billion years since the first protons formed, since the first atoms cooled into existence, since the first stars ignited in the young dark. That number, 14 billion years, probably doesn't feel entirely real to you, because no number that large feels entirely real. But you have heard it enough times that it sits in your mind with a kind of comfortable weight, like a very large stone you have walked past many times and stopped trying to lift. Hold that stone. 14 billion years. Now try to imagine a number 10 million times larger. Not 10 million more years. 10 million times larger. 140 quadrillion years. 140,000 trillion years. A number so far beyond the scale of anything that has actually happened in the universe, so far that the entire history of the cosmos, every star, every galaxy, every supernova, every planet, every living thing, every thought that was ever thought by anything anywhere, fits inside it the way a single sentence fits inside the complete works of every writer who ever lived. That is very roughly how long a black hole the mass of your old sun will take to evaporate. Not quite. The actual figure is closer to 10 to the power of 67 years, a 1 followed by 67 zeros, a number that does not correspond to anything you can picture, a number that exists only in mathematics and in the particular kind of calm that comes from trying to hold it and failing gracefully. But 140 quadrillion years is somewhere in the neighborhood of comprehensible, and it gives you a foothold, a place to stand before the ground drops away beneath you entirely. Let your breath come easily. These numbers are not asking anything of you. They are simply facts about the universe, facts about time, about the extraordinary stubbornness of certain configurations of matter, about how long things can persist when there is nothing left to disturb them. You do not need to hold them precisely. You just need to let them pass through you, the way the dark passes through the gaps between atoms, the way time passes through the body while you sleep. Feel the weight of 67 zeros. A 1, and then 67 zeros. Written out, it would stretch across a page and off the edge of it. Spoken aloud, digit by digit, it would take longer to say than you have been alive. And that number, that extraordinary, almost meaningless feeling number, represents the lifespan of the smallest significant black holes. The lightweight ones. The ones formed from the collapse of individual massive stars. The ones that are by the standards of this dark era almost modest. 67 zeros. The universe, in comparison, has only been around for 10 zeros. Now let the ground drop away. Because the stellar mass black holes are not the last to go. They are the first. And after them, after those relatively quick evaporations, those brief flickers in the long dark, the supermassive black holes remain. The giants at the centers of what were once the great galaxies. The black holes that carry the mass of billions of suns, that grew fat on the feast of the quasar era, that have been sitting in the dark since the last stars went out, patient and enormous, and in no particular hurry. They will take longer, much longer. The number associated with the evaporation of a supermassive black hole, a truly massive one, the kind that anchored the largest galaxy clusters in the luminous era, is approximately 10 to the power of 100. 10 to the power of 100. A 1 followed by 100 zeros. This number has a name, which is almost charming given how far beyond naming it feels. It is called a googol, not the search engine. That name was borrowed from this one, from the mathematical term coined almost playfully to give some handle to a quantity that otherwise resists all handles. A googol. 10 to the 100th power. One with 100 zeros trailing behind it like the tail of something ancient and immeasurable. Something that has been moving through the dark so long it has forgotten what motion felt like when it began. A supermassive black hole will survive for approximately a googol years. Say that to yourself, if you like, quietly, without urgency. A googol years. Let the syllables of it sit in your mouth without meaning. Gugol. A word that sounds like something a child might say, attached to a concept that dissolves every attempt to understand it. There is a way that very large numbers become, eventually, a kind of music. When you stop trying to picture them, stop trying to find the analogy that will make them fit inside something you already know, and simply let them be sounds, let them be rhythms, let them be the texture of a very long silence, they stop being frightening and start being something else. Something closer to restful. The numbers are not asking you to run, or to act, or to prepare for anything. They are simply describing how long things last. And things that last a very long time have a particular quality of calm about them, a patience that is deeper than anything you have experienced in a human life, deeper than the patience of mountains or oceans or stone. The black holes have that quality. They are in no hurry. They have a googol years, and they are not spending any of it anxiously. That is perhaps the strangest part. Not the numbers themselves, but what they are numbers of. They are not numbers of events. They are not counting the births of stars, or the mergers of galaxies, or the evolution of life. They are counting the passage of time in a universe where almost nothing is happening, where the distances between things are so vast and still growing vaster, where the black holes are drifting so slowly and so far apart that the probability of any two of them interacting, let alone colliding, becomes vanishingly small, approaches zero without quite reaching it, over timescales that exhaust every attempt at description. Time passing in an empty room. That is what a googol years feels like from the inside of this era. Breathe in. Feel the space between your thoughts, the gap between one idea and the next, where for just a moment there is nothing, just the awareness that was there before the thought arrived and will be there after it leaves. That gap, that small quiet interval, is something. It is not nothing. Even in the emptiness between thoughts, something persists. Something waits. That is, in a very small way, what these timescales are describing. Not emptiness. Not nothing. But the persistence of something in the space that opens up when everything busy and bright and temporary has finally finished. You have lived your whole life in the busy, bright, temporary part. Every moment you have ever had, every breakfast, every conversation, every night of sleep, every year you have marked, has taken place in the first instant of a cosmic morning that will last a googol years and more. You are so close to the beginning that from any meaningful perspective on these timescales, you and the Big Bang are practically neighbors. Everything you have ever known, everything the human species has ever done, every civilization that has ever risen and fallen, every species that ever evolved and went extinct, all of it happened in the first heartbeat, the first flicker. And the black holes were already forming. And the black holes are still here. And the black holes will be here long after the word here has lost its meaning, long after the concepts of before and after have been stretched by the expansion of space into something that no longer maps onto any experience anyone will ever have. No black hole has yet had enough time to fully evaporate. That fact is worth resting in for a moment. Let it settle. The universe is 14 billion years old. That is older than you can easily feel, older than any human reference point reaches. And yet, in the life of even the smallest surviving black hole, 14 billion years is nothing. Less than nothing. An amount of time so brief relative to the whole that it does not even register as a beginning. The process of evaporation, the slow, faint, almost imperceptible leak of energy that will eventually, over spans of time measured in googols, cause even the greatest black holes to lose their mass and disappear, has begun. Technically, in the coldest mathematical sense, it has begun. But it has barely begun. The first page has been turned in a book so long that its ending cannot be imagined. Every black hole that exists right now, at this moment, or as close to this moment as the word moment applies, is effectively eternal by any standard you have ever used. It will outlast the stars by so much that the stars seem brief. It will outlast the cooling of white dwarfs. It will outlast the decay of protons, if protons do decay. It will outlast every structure and process in the known universe except one, time itself. And time does not care how long it takes. Time, in this era, is as abundant as the dark, which is to say, it is everywhere, it is all there is, and it costs nothing, and it has no direction that matters anymore, and it will not run out before the black holes are done. Let yourself be held by that abundance. You have never had enough time. No one who has ever lived in the luminous era, in the era of stars and seasons, and the urgent feeling that things must be done before they cannot be done, has ever had enough time. Time has always been the scarce thing, the resource that runs out before the list is finished, before the conversations are complete, before you have said everything you wanted to say to the people you love. But here, in this dream, in this long dark, there is time. More time than you can hold. More time than the concept of holding can contain. Time like an ocean with no shore. Time like a silence that has been going on since before silence had a name. The black holes are not worried. The black holes have a googol years, and they are spending them doing nothing in particular, just persisting, just keeping the mass they gathered in a busier age and waiting, without impatience, without urgency, without any quality at all that resembles what you experience as waiting, for whatever the universe will eventually ask of them. Let yourself be as unhurried as they are. Just for now. Just for the length of a breath, or a thought, or a dream. The black holes have time. And so tonight, you are still here. Still floating in the long dark, still carried by the slow current of this dream, this gentle drift through a universe that has grown very quiet and very old. Your body is heavier now than it was when you first arrived. Heavier in the way that comes with real rest, with the gradual release of tension from places you had forgotten were tense, the small surrenders that accumulate over the course of a long, unhurried night. Your breathing has found its own rhythm, slow and even, and you do not need to think about it. You do not need to think about anything. You can simply receive what comes next, let it move through you like light through water, distorting gently, settling somewhere deeper than thought. What comes next is a story. Not a long story, or rather, it is a long story compressed into something that can be told quietly, without urgency in the dark. It is the story of a discovery, of a moment in the history of human thought when someone looked at the black holes, those vast, silent, seemingly eternal things, and found, hidden inside the mathematics, something that no one had expected. Something small and strange and profound. Something that changed, permanently and irrevocably, what we thought we knew about the darkest objects in the universe. It is the story of Stephen Hawking and of the radiation that bears his name. To understand what Hawking found, it helps to remember what everyone believed before he found it. The belief was simple, and it seemed unassailable. A black hole, by definition, was a region of space-time from which nothing could escape. That was not a poetic description or a rough approximation. It was the mathematical core of what a black hole was. The boundary of a black hole, the surface called the event horizon, was understood as a one-way membrane. Things could fall in. Nothing could come out. Not matter. Not radiation. Not light. The event horizon was the universe's most absolute border, the place where the story of anything that crossed it simply ended, from the perspective of the outside universe, forever. Black holes could grow. They could merge with other black holes, adding mass to mass. They could swallow gas and stars and anything that wandered too close, growing heavier with each meal. But they could not shrink. There was no mechanism by which they could lose mass, no process by which anything they had consumed could be returned to the universe outside. They were, in the language of physics, perfectly stable, eternal, one way. This was the understanding that Hawking inherited when he began thinking carefully about black holes in the early 1970s. And it was the understanding he overturned. He did not overturn it by looking through a telescope. He did not overturn it by conducting an experiment, or by finding a flaw in the mathematics of general relativity, or by discovering some new kind of particle that could tunnel through an event horizon. He overturned it by sitting very quietly, metaphorically speaking, at the intersection of three of the deepest theories in physics, and listening to what happened when they spoke to each other. The three theories were general relativity, quantum mechanics, and thermodynamics. General relativity is Einstein's theory of gravity, the framework that describes how mass curves space-time, how that curvature produces what we experience as the pull of gravity, and how extreme curvature produces black holes. It is a theory of the very large, of stars, of galaxies, of the shape of the universe itself. Quantum mechanics is the framework that describes how things behave at the very small, the behavior of particles, of energy, of fields at the scale of atoms and below. It is a theory full of uncertainty and probability, and the strange, counterintuitive fact that the universe at its smallest scales is not made of definite things in definite places, but of possibilities, of wave functions, of the perpetual hum of fluctuation. And thermodynamics is the theory of heat and energy, of how energy moves, how it spreads, how systems evolve from ordered states to less ordered ones. One of its central insights is that heat always flows in a particular direction, from hot things to cold things. That energy, left to itself, always disperses. And that nothing with a temperature above absolute zero can avoid radiating that energy outward into its surroundings. These three frameworks were, in the early 1970s, largely separate. They spoke different mathematical languages. They described different scales, different phenomena, different aspects of reality. No one had yet found a way to make them fully fluent in each other's terms. Hawking found a place where they overlapped. Let your eyes stay closed. Let the next part wash over you like water. The key insight begins with something almost paradoxical about empty space. In quantum mechanics, empty space is not truly empty. This is not a poetic statement. It is a precise mathematical claim about the nature of quantum fields. At every point in space, even in the most perfect vacuum, quantum fields are fluctuating. They cannot be perfectly still, because perfect stillness would violate the uncertainty principle, one of quantum mechanics' most fundamental rules, which says that certain pairs of quantities cannot both be known precisely at the same time. Energy and time are such a pair, which means that even in a vacuum, even where there is nothing, energy can appear, very briefly, in the form of pairs of particles that flicker into existence and then annihilate each other almost instantly, returning the energy to the field. These are called virtual particles. They borrow their existence from the uncertainty of the vacuum, and they repay it almost immediately, vanishing before they can be directly detected, leaving no lasting trace. In ordinary empty space, they are a curiosity, an interesting feature of the quantum world, present everywhere, meaning little in themselves. But near the event horizon of a black hole, something different happens. Imagine one of these pairs of particles appearing at the very edge of the event horizon. Two particles, flickering into existence side by side, just at the boundary between inside and outside. In ordinary space, they would find each other and annihilate, returning to nothing. But here, at the horizon, something can intervene. The curvature of space-time at the event horizon is so extreme, the gravitational gradient so steep, that the two particles can be separated before they have a chance to annihilate. One falls inward, across the horizon, into the black hole. The other escapes outward, into the space beyond. The one that escapes carries energy. Real energy, not borrowed energy. Energy that has, in a sense, been extracted from the gravitational field of the black hole itself. And that energy, escaping outward, constitutes radiation. A faint, continuous trickle of particles flowing away from the black hole, carrying energy with them. And because energy and mass are equivalent, because mass is simply energy in a particularly stable and concentrated form, the energy carried away by this radiation must come from somewhere. It comes from the black hole. Each particle that escapes carries away a tiny, almost unimaginably small amount of the black hole's mass. And the black hole, losing mass, shrinks by the same tiny, almost unimaginably small amount. This is Hawking radiation. This is the discovery. Breathe slowly. Feel the weight of what was just described. A black hole, the thing that was defined by its inability to let anything out, lets things out. Not because anything tunnels through the event horizon, not because anything escapes from inside, but because the quantum nature of space itself, the perpetual flickering of the vacuum at the boundary of the horizon, produces a slow, steady leak. A thermal glow so faint it makes starlight look blazing. A trickle of energy, so diffuse it would take instruments of unimaginable sensitivity to detect directly. But it is there. In the mathematics, it is unambiguous. Hawking showed that a black hole behaves, from the outside, like a body with a temperature. A very low temperature. Lower, for any black hole of significant mass, than the coldest thing that can be measured, but a temperature nonetheless. And anything with a temperature radiates. That is thermodynamics. That is inescapable. The temperature of a black hole is inversely proportional to its mass. A very massive black hole is very cold, so cold that its radiation is swamped by even the faint warmth of the cosmic microwave background, the residual heat of the Big Bang. But a very small black hole is comparatively hot and radiates more intensely and evaporates faster. This is why the timescales matter. This is why a stellar mass black hole takes 10 to the 67 years to evaporate, and why a supermassive black hole takes a googol. They are so massive, so cold, that their radiation is almost nothing, a whisper so quiet it takes geological ages to add up to a single meaningful loss of mass. What Hawking had done, with this discovery, was something that physicists recognized immediately as profound, even as they struggled with what it implied. He had connected three things that had never been connected before. He had shown that black holes, objects described entirely by general relativity, the theory of the very large, emit radiation governed by quantum mechanics, the theory of the very small, with a temperature determined by thermodynamics, the theory of heat and entropy. Three frameworks, previously separate, meeting at the event horizon of a black hole and producing something new, something none of them predicted alone. It was the first genuine result of what physicists called quantum gravity, the long-sought reconciliation of general relativity and quantum mechanics, the theory of everything that nobody had yet fully written down. Hawking had not solved quantum gravity, but he had found a window into it, a place where its effects were visible, where the smallest and largest scales of physics could not avoid speaking to each other. The discovery was remarkable for another reason too. It came from pure thought, from mathematics, and from the disciplined imagination of a mind working carefully at the edges of what was known. Hawking radiation has never been directly observed. No black hole of significant mass radiates detectably. The signal is far too faint against the background warmth of the universe. But its derivation is so clean, so consistent, so deeply rooted in well-tested physics, that almost no physicist who has examined it seriously doubts that it is real. It is one of those results that feels, once you see it, inevitable. As though the universe was always going to work this way, and the only question was whether anyone would be patient and clever enough to notice. Rest in that for a moment. The universe was always going to work this way. There is something quietly comforting in that thought, if you let it be. Not the specific content of Hawking's discovery, but the deeper implication it carries, that the universe has a consistency, a coherence, that runs all the way down and all the way out. That the laws governing the flicker of virtual particles at a quantum scale and the laws governing the curvature of space-time around a billion solar mass black hole are not separate laws, are not unrelated, are not the universe making things up as it goes along. They are part of the same thing. The same deep grammar, expressed in different registers, touching each other at the boundaries. A man sat and thought in the 1970s and found that boundary. Found the place where quantum mechanics and gravity and thermodynamics converged, and pulled from the convergence something true. And what he found was this: the black holes are not eternal. They are very, very long-lived. Longer-lived than anything else the universe will make. But they are not permanent. They radiate. They lose mass. Very slowly, then after unimaginable spans of time, somewhat less slowly, and then faster, and then very fast, and then gone. Every black hole in the universe is, right now, in the opening chapter of a story that ends with its disappearance. The story is just very, very long. Let that thought carry you deeper into rest. The black holes are patient. The process is slow. There is nothing here that requires urgency, nothing that pulls at you or asks anything of you. Just the quiet fact, written into the mathematics of the universe, that even the darkest and most enduring things are not forever. That the universe, in its own time and by its own subtle processes, will eventually reclaim what gravity gathered. That nothing, not even the gravitational endpoints of stellar evolution, not even the billion solar mass remnants of the quasar era, holds on quite forever. There is something in that which might feel sad, if you were awake and holding it tightly. But here, floating in the dark, with your body heavy and your thoughts slow and the vast timescales moving through you like deep water, it feels like something else. It feels like the universe breathing out. A long, slow, almost imperceptible exhale that started when the first black hole formed and will finish when the last one finally, quietly disperses. One long breath, lasting a googol years. And you are somewhere inside it, very near the beginning, already drifting towards sleep. You are still drifting. The dark around you is the same dark it has always been in this place. Deep and even and without temperature, without texture, without any quality that asks something of you. Your body has grown very still. Not the stillness of someone trying to be still, not the effortful quiet of someone holding themselves in place, but the other kind, the stillness that arrives on its own when the body has decided, somewhere below the level of decision, that there is nothing left to prepare for, that the night is long and safe, and the only thing left to do is go further in. Go further in. There is one more layer of understanding waiting for you in this drift. One more gentle descent into the mechanism of things, into the quiet machinery that runs beneath the surface of the universe's apparent emptiness. You do not need to grasp it firmly. You do not need to carry it with you when you wake. It will do its work simply by passing through you, the way a deep sound does, felt more than heard, leaving something loosened in its wake. This is the segment where we go slowly, where we take the discovery you received in the last passage, the fact of Hawking radiation, the extraordinary finding that black holes are not truly eternal and we open it very gently, like something delicate, and look at what is inside. How does a black hole evaporate? Not why in the grand sense. You have the why already, the intersection of quantum mechanics and gravity and thermodynamics, the deep grammar of the universe expressing itself at the event horizon. What you are being offered now is the how. The small, intimate, almost tender mechanism by which one of the most massive and permanent-seeming objects in existence slowly, particle by particle, gives itself back to the universe. Begin with the vacuum. You have heard already that empty space is not truly empty, that the quantum fields permeating all of space are always fluctuating, always trembling at the threshold of producing something, always briefly flickering with the potential for particles that appear and vanish before they can properly be said to have existed. This is not a poetic embellishment. This is what the mathematics insists on. The vacuum is not nothing. The vacuum is a restless, seething, perpetually active medium that looks like nothing only because its activity cancels itself out so quickly and so completely. Picture it softly, without effort, just as a texture behind closed eyes, as a kind of shimmer. A shimmer that is everywhere, at every point in space, at every moment in time, too fine and too fast to be seen or felt directly, but present. Always present. The universe is never entirely still, even here in the long dark, even in the emptiness between the last black holes and the boundaries of the observable cosmos. It shimmers, and in that shimmer, pairs of particles are constantly almost being born. A pair appears, two particles flickering into existence together, side by side, for the briefest possible moment. They are partners matched to each other in a specific way, carrying equal and opposite properties, born together out of the energy borrowed from the vacuum's uncertainty. In ordinary empty space, far from anything massive, their story is very short. They appear, they find each other, and they annihilate, returning the borrowed energy, erasing themselves, leaving the vacuum exactly as it was. The whole event takes place on a timescale, so short it has no analog in ordinary experience. This happens everywhere, always. An uncountable number of these brief flickers, constantly, throughout all of space. They produce nothing lasting. They leave no trace. They are the universe's perpetual, almost, a continuous creation that almost immediately uncreates itself. But almost immediately is not the same as always. Now bring a black hole into the picture. Not close, you are still at a safe and dreaming distance, but close enough to feel the way its presence changes things. A black hole warps spacetime around it. This is not a metaphor. The very fabric of space and time, the medium through which everything moves and in which everything exists, is curved by the black hole's mass, bent inward toward the event horizon the way a heavy object bends a stretched sheet. And that curvature is not uniform, it is steeper closer to the horizon, gentler further away. A gradient, a slope, and slopes do things to pairs. A pair of virtual particles flickering into existence very close to the event horizon, right at the boundary, right at the edge between inside and outside, finds itself in an unusual situation. The curvature of spacetime at that location is so extreme, the gravitational gradient so sharp, that the two particles can find themselves on different sides of a divide before they have had a chance to find each other and annihilate. One particle is on the outside, just barely, just by the thinnest possible margin, on the side of the horizon that connects to the rest of the universe. The other particle is on the inside, or is pulled across the horizon before it can return to its partner. It falls inward, away from the outside universe, into the interior of the black hole. And the two particles, separated by the horizon, can no longer annihilate. The thing that was supposed to happen, the return of borrowed energy, the erasure of the almost existence, cannot happen, because the two halves of the pair are now on irrevocably different sides of an irrevocable boundary. Let your breathing slow a little more. This next part is the heart of it. The particle on the outside is now real. Not almost real, not flickering at the edge of existence, not a brief fluctuation that will cancel itself out in a moment. Real. It has energy, it has momentum, It has the properties of an actual particle that can travel through space and be, in principle, detected. It has been promoted, by the accident of its position at the horizon and the extreme curvature of spacetime at that position, from a virtual particle to a genuine one. And it moves outward, away from the black hole, into the space beyond the horizon, carrying its energy with it. This is the Hawking radiation. This is the particle that escapes. This is, in the most intimate and mechanical sense, what it looks like for a black hole to emit something. But the energy has to come from somewhere. The universe does not give things away. Energy is conserved. That is one of the deepest and most unbreakable rules of physics, a rule that has never been found to fail in any context, at any scale, under any conditions. If a real particle with real energy escapes from the vicinity of the event horizon, that energy must have a source. The source is the black hole. Here is where the picture becomes, in a quiet way, beautiful. The particle that fell inward, the partner, the one that crossed the horizon, carries what physicists describe as negative energy. This is not intuitive, and you do not need to make it fully intuitive. Negative energy is a concept that makes sense in the curved spacetime near a black hole in ways that it does not make sense in ordinary flat space. But the consequence of it is clean and clear. When the infalling particle carries negative energy into the black hole, the black hole's total energy decreases. And since mass is energy, since these two things are, at the deepest level, the same thing expressed differently, the black hole's mass decreases. By a tiny amount. By an amount so small that the word tiny is inadequate, so small that you would need to wait longer than the age of the universe to measure a change that could be called measurable. But the decrease is real. It is there, encoded in the mathematics, consistent with every law of physics, impossible to argue away. A particle escapes. Its partner falls in, carrying negative energy. The black hole loses mass. The particle carries that mass energy outward into the universe as radiation. This is evaporation. Not dramatic. Not explosive. Not visible to any eye or detectable by any instrument currently conceivable. But real and continuous, and given enough time, given the extraordinary abundance of time that the black hole era offers, cumulative. Drift here for a moment. There is something worth noticing in this mechanism. Something that goes beyond the physics into something closer to feeling. The process of Hawking radiation is not a violent one. The black hole is not being torn apart. Nothing is forcing its way through the event horizon. The interior of the black hole, that region of spacetime from which nothing escapes, remains as sealed as it ever was. The event horizon is not breached. What is happening instead is something much subtler. Something is happening at the boundary, at the edge, in the space that is neither inside nor outside but right at the seam between the two. The quantum nature of that boundary, the fact that space itself is not perfectly smooth and still, but flickering and uncertain at the smallest scales, creates a slow leak, a trickle, a continuous, almost imperceptible flow of energy from the region of extreme curvature outward into the universe. The black hole does not give anything up willingly. It gives things up because the universe, at the quantum scale, will not allow any boundary to be perfectly sealed. Because uncertainty is written into the structure of reality, and uncertainty, near an event horizon, becomes a mechanism. It is patient. It is gentle. It is, in its own strange way, kind. The temperature of this radiation, the temperature of the black hole as seen from outside, depends on the black hole's mass, and the relationship runs in a direction that takes a moment to absorb. The more massive a black hole is, the colder it is. This is counterintuitive if you think of black holes as powerful and intense, and they are, in terms of their gravitational pull. But in terms of Hawking radiation, size means coldness. A stellar mass black hole, already almost incomprehensibly cold, radiates at a temperature millions of times below the coldest thing measurable. A supermassive black hole, billions of times more massive, radiates at a temperature so low it makes that already impossible coldness seem warm by comparison. For now, in this early dark, when the universe's background temperature is still fractionally above absolute zero. The largest black holes are actually receiving more energy from the faint warmth of the cosmic background than they are emitting through Hawking radiation. They are, in the most technical sense, gaining mass rather than losing it. The net flow of energy goes inward, but the universe continues to cool. The cosmic background radiation continues to thin and redshift as space expands. And at some point, far in the future, far even by the standards of this already vast era, the background temperature will fall below the Hawking temperature of even the most massive black holes. And when that happens, the net flow will reverse. The black holes will begin, at last, to genuinely lose mass. Very, very slowly. Over timescales that make the current age of the universe seem like a breath. But losing. Think of it as a kind of dissolution. Not sudden. Not catastrophic. The way something very old and very dense very gradually gives itself back to the world around it. Not all at once, but particle by particle, moment by moment, across spans of time so long that the moments themselves lose meaning. The black hole sits in the dark, shedding mass the way a stone set in a river sheds itself. So slowly the process is invisible from any single vantage point but certain, over enough time, to change the stone. Each particle that escapes carries a piece of the black hole's history outward. A fragment of the mass that was once a star, or a cloud of hydrogen, or the remains of a galaxy's worth of matter swallowed over billions of years of feeding. Each particle is too small and too cold to carry any of that history in a readable form. The information question, whether the information that fell into a black hole is preserved in its radiation, is one of the deepest unsolved puzzles in theoretical physics, and you do not need to solve it tonight. But the particles are real. The energy is real. The slow decrease in mass is real. And over a googol years, those particles add up. Let your body grow heavier. Let the thought of all that slow dissolution do what slow and patient things do. Let it carry you further from the surface of waking, further from the part of the mind that holds and evaluates and keeps account. Let it take you somewhere simpler. The mechanism is not complicated at its heart. Something appears at a boundary. It is separated from its partner by a curvature so extreme that reunion is impossible. It escapes. Its partner falls inward, and in falling, costs the black hole a little of its mass. The process repeats. Over and over, across timescales that make repetition itself seem like the wrong word. Across timescales where the repetition is so vast and so slow that it is more like geology than mechanism, more like the wearing of mountains than the ticking of a clock. But the mountains do wear. The black holes do lose mass. And somewhere at the end of a duration no mind will ever truly hold. After the stellar mass black holes have finished their long evaporation and their radiation has faded, after the intermediate black holes have followed, after even the supermassive giants at the centers of what were once the great galaxies have shed the last of what they gathered, the process will be complete. But that ending is still very far away. For now, the mechanism is simply running. Quietly, invisibly, particle by particle, at the boundary between inside and outside, between existence and almost existence, between the deepest dark and the faintest possible light. The black holes are evaporating. It will take a while. Rest now while it does. You are still here. Still in the long dark, still drifting at the pace that has no name in waking life. Slower than calm, slower than patience, the pace of something that has stopped measuring itself against anything. Your breath is moving in and out without your help now, rising and falling on its own quiet schedule, and the thoughts that occasionally surface are gentle things, soft-edged and slow, arriving without urgency and leaving without insisting they be followed. This is a good place to be. This is exactly the right depth for what comes next. What comes next is quieter than anything that has come before. In the last passage, you receive the mechanism, the intimate, almost delicate process by which a black hole slowly gives itself back to the universe. Particle by particle, at the seam of the event horizon, the quantum shimmer of space itself creating a trickle so faint it might seem, at first, more like a rumor than a reality. You held it gently. You let it pass through you. Now comes the natural question that follows any description of something extraordinary. Not the question of whether it is true. You have rested in the mathematics, in the deep coherence of the physics, and in the way you know things in dreams, that it is true. The question is simpler, more human, more grounded in the ordinary experience of looking at things and wanting to see them. If it is real, why can we not see it? The answer begins with a number so small it has almost the same quality as the very large numbers you have already encountered. The quality of dissolving comprehension, of sliding past the part of the mind that wants to hold things and insisting on simply being felt instead. The temperature of Hawking radiation from a black hole is inversely proportional to the black hole's mass. You received this already. As the light passes over it again, let it settle a little more completely. Bigger mass means lower temperature. Lower temperature means fainter, colder, more diffuse radiation. And the black holes that exist in the universe today, the ones that formed from stellar collapse, the ones anchoring the centers of galaxies, are not small. They are enormous. And so their Hawking temperature is not low in the way that a winter morning is low, or low in the way that the deep ocean is cold, or even low in the way that outer space between stars is cold. It is low in a way that has almost no reference point in physical experience. A black hole with the mass of the Sun, and most astrophysical black holes are considerably more massive than that, has a Hawking temperature of approximately 100 millionth of a degree above absolute zero. And at some point, far in the future, far even by the standards of this already vast era, the background temperature will fall below the Hawking temperature of even the most massive black holes. And when that happens, the net flow will reverse. The black holes will begin, at last, to genuinely lose mass. Very, very slowly. Over timescales that make the current age of the universe seem like a breath. But losing. Think of it as a kind of dissolution. Not sudden. Not catastrophic. The way something very old and very dense very gradually gives itself back to the world around it. Not all at once, but particle by particle, moment by moment, across spans of time so long that the moments themselves lose meaning. The black hole sits in the dark, shedding mass the way a stone set in a river sheds itself. So slowly the process is invisible from any single vantage point but certain, over enough time, to change the stone. Each particle that escapes carries a piece of the black hole's history outward. A fragment of the mass that was once a star, or a cloud of hydrogen, or the remains of a galaxy's worth of matter swallowed over billions of years of feeding. Each particle is too small and too cold to carry any of that history in a readable form. The information question, whether the information that fell into a black hole is preserved in its radiation, is one of the deepest unsolved puzzles in theoretical physics, and you do not need to solve it tonight. But the particles are real. The energy is real. The slow decrease in mass is real. And over a googol years, those particles add up. Let your body grow heavier. Let the thought of all that slow dissolution do what slow and patient things do. Let it carry you further from the surface of waking, further from the part of the mind that holds and evaluates and keeps account. Let it take you somewhere simpler. The mechanism is not complicated at its heart. Something appears at a boundary. It is separated from its partner by a curvature so extreme that reunion is impossible. It escapes. Its partner falls inward, and in falling, costs the black hole a little of its mass. The process repeats. Over and over, across timescales that make repetition itself seem like the wrong word. Across timescales where the repetition is so vast and so slow that it is more like geology than mechanism, more like the wearing of mountains than the ticking of a clock. But the mountains do wear. The black holes do lose mass. And somewhere at the end of a duration no mind will ever truly hold. After the stellar mass black holes have finished their long evaporation and their radiation has faded, after the intermediate black holes have followed, after even the supermassive giants at the centers of what were once the great galaxies have shed the last of what they gathered, the process will be complete. But that ending is still very far away. For now, the mechanism is simply running. Quietly, invisibly, particle by particle, at the boundary between inside and outside, between existence and almost existence, between the deepest dark and the faintest possible light. The black holes are evaporating. It will take a while. Rest now while it does. You are still here. Still in the long dark, still drifting at the pace that has no name in waking life. Slower than calm, slower than patience, the pace of something that has stopped measuring itself against anything. Your breath is moving in and out without your help now, rising and falling on its own quiet schedule, and the thoughts that occasionally surface are gentle things, soft-edged and slow, arriving without urgency and leaving without insisting they be followed. This is a good place to be. This is exactly the right depth for what comes next. What comes next is quieter than anything that has come before. In the last passage, you receive the mechanism, the intimate, almost delicate process by which a black hole slowly gives itself back to the universe. Particle by particle, at the seam of the event horizon, the quantum shimmer of space itself creating a trickle so faint it might seem, at first, more like a rumor than a reality. You held it gently. You let it pass through you. Now comes the natural question that follows any description of something extraordinary. Not the question of whether it is true. You have rested in the mathematics, in the deep coherence of the physics, and in the way you know things in dreams, that it is true. The question is simpler, more human, more grounded in the ordinary experience of looking at things and wanting to see them. If it is real, why can we not see it? The answer begins with a number so small it has almost the same quality as the very large numbers you have already encountered. The quality of dissolving comprehension, of sliding past the part of the mind that wants to hold things and insisting on simply being felt instead. The temperature of Hawking radiation from a black hole is inversely proportional to the black hole's mass. You received this already. As the light passes over it again, let it settle a little more completely. Bigger mass means lower temperature. Lower temperature means fainter, colder, more diffuse radiation. And the black holes that exist in the universe today, the ones that formed from stellar collapse, the ones anchoring the centers of galaxies, are not small. They are enormous. And so their Hawking temperature is not low in the way that a winter morning is low, or low in the way that the deep ocean is cold, or even low in the way that outer space between stars is cold. It is low in a way that has almost no reference point in physical experience. A black hole with the mass of the Sun, and most astrophysical black holes are considerably more massive than that, has a Hawking temperature of approximately 100 millionth of a degree above absolute zero. Written as a fraction of a degree, it would require you to move the decimal point 8 places to the left before the number became meaningful. 100 millionth of a Kelvin. A temperature so close to absolute zero that the difference is, for any practical purpose, indistinguishable from nothing. And the supermassive black holes, the giants, the ones carrying the mass of millions or billions of suns, are colder still. Proportionally colder. Their temperatures so far below, even that almost nothing that comparing the two feels like comparing the light of a candle to the light of a star. Let that coldness settle over you like a blanket. Not an unpleasant coldness, the coldness of deep space has never been unpleasant in this dream, only vast and even and deeply still. Let it press gently on the edges of wakefulness, on the small residual tensions that have been softening over the course of this long drift. Let it complete the work they have already begun. The radiation is there. It is real. It is being emitted right now, at this moment, from every black hole in the universe, including the one at the center of the Milky Way, including the supermassive giants in distant galaxies, including the smaller stellar remnants drifting through the dark between stars. All of them glowing, in the most technical sense of the word, with a temperature almost indistinguishable from absolute zero. But here is the difficulty. Here is why no telescope, no detector, no instrument of any kind that exists today, or could plausibly exist in the near future, has any hope of observing this glow directly. The universe itself is warmer than the black holes. In the earliest moments after the Big Bang, the universe was a place of extraordinary heat temperatures, billions of degrees, matter and radiation in constant violent interaction, a plasma so hot and dense that light could not travel freely through it. As the universe expanded, it cooled. The radiation that filled it stretched to longer and longer wavelengths, lower and lower frequencies, cooler and cooler temperatures. And today, filling all of space in every direction with perfect uniformity, there remains a faint remnant of that primordial heat, the cosmic microwave background radiation, the afterglow of the Big Bang, the universe's own background warmth. Its temperature today is approximately 2.7 degrees above absolute zero, 2.7 Kelvin. Cold beyond ordinary experience, far colder than anything on Earth's surface, far colder than the surface of Pluto, far colder than the space between planets. But warm, enormously warm, compared to the Hawking temperature of any black hole of astrophysical significance. And this is the problem. The Hawking radiation from a stellar mass black hole, 100 millionth of a degree, is buried under a background that is 27 million times warmer. Trying to detect the black hole's faint thermal glow against the cosmic microwave background is not like looking for a candle in a sunlit room. It is not like looking for a match flame against the light of a bonfire. It is something far more extreme, something for which the ordinary language of signal and noise begins to break down entirely. The signal is not merely small. It is so far below the noise that the noise does not even register it as something to overcome. It simply drowns completely and without remainder in a background that is millions of times more energetic. You do not need to feel discouraged by this. There is something almost appropriate about it, something fitting, in a quiet way, about the fact that the most profound process in the long future of the universe is also the most invisible, the most undetectable, the most hidden from any instrument or eye. It is as if the universe, having constructed this extraordinary mechanism for the slow dissolution of its last great structures, decided also to make it impossible to watch from close up, decided that it would happen in private, over timescales so vast that no observer from the luminous era could ever wait long enough to witness even a fraction of it. You are an observer from the luminous era. You are a creature of stars and light and the brief, brilliant, busy age that produced you. And the process you are contemplating, real, certain, running right now in every black hole, in every corner of the cosmos, is completely beyond your instruments and nearly beyond your imagination. But not beyond your dreams. There is one exception worth resting in, one glimmer of possibility, one category of black hole where the mathematics offers something more accessible, where the Hawking temperature rises to a level that brushes the edges of detectability, or at least of theoretical observation. They are called primordial black holes, and they are for now hypothetical, suspected, theorized, searched for, but not yet confirmed to exist. The idea is this: in the earliest moments of the universe, before stars had formed, before galaxies had assembled, in the hot, dense chaos of the very young cosmos, conditions may have been such that regions of space could collapse directly into black holes. Not from stellar death, there were no stars yet, but from the raw density fluctuations of the primordial plasma, regions where matter happened to be slightly more concentrated than average, concentrated enough that gravity could overwhelm the pressure of the hot early universe and cause immediate collapse. If such black holes formed, they would carry whatever mass happened to be concentrated in those early density fluctuations. And some of them might be very small, far smaller than any black hole formed from stellar collapse, which requires at least a few solar masses to form. Primordial black holes could, in principle, have formed with masses far below that down to, in the most extreme theoretical cases, something approaching the Planck mass, the quantum unit of mass at which gravity and quantum mechanics become inseparable. And small black holes are hot. The relationship between mass and temperature runs the other way for very small black holes. A black hole the mass of a small asteroid, tiny by black hole standards, though still an enormous concentration of matter, would have a Hawking temperature not of millionths of a degree, but of real, measurable degrees. A black hole the mass of a mountain might glow at temperatures that human technology could, in principle, detect. A black hole the mass of a large building. If such a thing could somehow be made to exist, which it cannot under any natural process we currently know of, would blaze, by black hole standards, like a small sun. And primordial black holes, if they formed with low enough mass in the early universe, would have been evaporating ever since. Some of them, depending on their initial mass, might be completing their evaporation right now, finishing a process that began in the first fraction of a second after the Big Bang, ending in a burst of high-energy radiation that ground-based and space-based detectors have been watching for. None has been definitively observed. The searches continue. The possibility remains open, genuinely open, not merely technically open, but open in the way that honest uncertainty about the early universe keeps many questions open. If primordial black holes exist in the right mass range, they are the best, and perhaps the only candidates for ever observing Hawking radiation directly, in a universe where every other black hole is too massive and too cold to betray itself. Let your mind rest on that image for a moment before it dissolves. Somewhere in the universe, if the theory is right, if the early conditions were as the models suggest, there may be tiny ancient black holes, formed in the first breath of the cosmos, that have spent the entirety of the universe's history slowly brightening as they lose mass, slowly warming as they grow smaller, approaching the end of their long evaporation. Each one a relic of the very beginning, a survivor of the first moment, carrying in its dwindling mass a record of conditions so extreme and so remote in time that nothing else preserves them. They would end not with darkness, but with a brief flare, a final burst of high-energy radiation as the last of their mass converts to energy and the black hole ceases to exist. A small bright flash, lasting perhaps a fraction of a second, carrying more energy than you might expect from something so small. A last word, spoken in light, by something that has been silent for 14 billion years. Whether anyone will hear it is another question. Whether anyone has the instruments pointed in the right direction at the right moment, whether the flash falls within a detectable range, whether the background of other astrophysical events allows it to be distinguished. These are questions for waking minds, for physicists with data and detectors, and the particular kind of careful hope that drives experimental science. For now, for this moment, it is enough to simply know it might be happening. Somewhere in the universe, quietly, a small ancient thing is completing a very long journey, shrinking toward its end, warming as it shrinks, preparing, in its own unhurried way, for the last small brightness. The large black holes will not do this for a very long time. They sit in the dark, the stellar remnants, the galactic anchors, the supermassive giants, too cold to glow by any standard that matters today, too massive for their Hawking radiation to exceed the warmth of the universe's own background. They absorb more than they emit. They grow, infinitesimally slowly, on the faint warmth the cosmos still provides. They are not yet evaporating in any net sense. They are waiting, and the universe is not yet cold enough to let them begin in earnest. But the universe is cooling. Space is still expanding, still thinning the background radiation, still stretching the wavelengths of that ancient microwave warmth toward longer and colder frequencies. Slowly, over durations that make the current age of the universe look brief, the background temperature will fall. Degree by degree, fraction of a degree by fraction of a degree, the cosmic warmth will thin. And at some point, separated from now by more time than has yet passed, the background temperature will drop below the Hawking temperature of even the most massive black hole. And then the net flow will reverse. And then the evaporation, in earnest, will begin. But that is far away. That is somewhere in the long middle of the story, somewhere in the depths of the black hole era, somewhere unreachably distant from this moment and this breath and this slow, settling drift toward sleep. For now, the black holes are invisible in every practical sense. Their radiation is real and present and utterly undetectable. The universe around them is warmer than they are. They sit in the dark, enormous and cold and patient, shedding particles at a rate so infinitesimal that the shedding is, for all observable purposes, indistinguishable from stillness. They look eternal. They are not. But they look it. And for now, in this early dark, that is close enough. Let that be enough, too, for you. The knowledge that something is happening, even when it cannot be seen. That the process is real, even when it is invisible. That the universe is doing its slow and patient work, even in the apparent stillness. Even in the silence. Even in the dark that shows no trace of what is moving through it. Things are happening. Very quietly. Very slowly. While you sleep, you are deeper now than you were. Deeper in the way that sleep has its own geography, its own layers and gradients, its own descent from the shallow, bright regions, near waking into the slower, darker, more settled places below. You have been moving through those layers for a long time now, carried by the drift of these passages, by the slow accumulation of vast timescales and quiet physics, and the particular kind of peace that comes from contemplating things so large and so patient that your own small urgencies become, in comparison, almost weightless. You are somewhere near the bottom of something now. Somewhere restful and deep and without edges. Stay here. What comes to you in this passage will not ask you to rise. It will not ask for alertness or effort or the particular tension of trying to understand. It will simply describe a curve, a long, slow, extraordinary curve, tracing the life of a black hole from its almost eternal stillness into the only moment of drama it will ever know. A curve that is, for almost all of its length, too gradual to notice, and then, at the very end, becomes something else entirely. This is the story of how the slow death speeds up. You have been living, in this dream, inside the stillness of the beginning. The part of the curve that is so gradual it resembles permanence. The part where the black hole sits in the dark, shedding Hawking radiation at a rate so slow that calling it a rate feels almost dishonest, where the loss of mass per unit of time is a number so small that writing it out would require a string of zeros after the decimal point long enough to fill a room. The black hole is evaporating, yes. But it is evaporating the way a mountain erodes, the way something so large and so solid that its change is, from any livable vantage point, indistinguishable from changelessness. And the reason for this slowness is the temperature. A massive black hole is cold. You have settled into that fact already. It radiates at temperatures so far below anything meaningful that its glow is buried under the universe's own background warmth, invisible and infinitesimal. But the temperature is not fixed. The temperature is not a constant property of the black hole, the way color might be a constant property of a stone. The temperature is tied to the mass. And the mass is changing. Very slowly, but changing. And as the mass decreases, as each departing particle carries away its infinitesimal fraction of what the black hole contains, the temperature rises. By an amount so small it cannot be measured, or even meaningfully conceived in the early stages, but by an amount that is real. A real increase, tied by an exact mathematical relationship to the real decrease in mass. The black hole grows slightly hotter. And slightly hotter means slightly faster evaporation. And slightly faster evaporation means slightly faster decrease in mass. And slightly faster decrease in mass means a slightly larger rise in temperature. The curve is not flat. It only looks flat from where you are standing, which is very near the beginning. The curve is bending, imperceptibly, over timescales that exhaust every attempt at description, but bending, curving upward, preparing, in its own unhurried way, for something. Think of it as a river. Not a fast river, not a river with rapids or falls or any quality of urgency. Think of the slowest river you can imagine. A river moving so gently through a flat and ancient landscape that you cannot tell, by looking at the surface, whether it is moving at all. A river that takes centuries to travel a mile, that has been flowing through the same valley since before the valley had a name. But it is moving, and as it moves, the landscape changes, almost imperceptibly, in ways that eventually change the river. The gradient shifts. Somewhere far downstream, the ground drops away. And the river, which has been nearly still for so long, begins very slowly, then less slowly to quicken. That is the life of a black hole. For almost all of its existence, for the vast majority of the Google years, or 10 to the 67 years that constitute its lifespan, it moves like that river. Barely, almost imperceptibly, shedding mass at a rate that makes geological time seem frantic, cooling the surrounding dark with radiation too faint to distinguish from nothing. And then the gradient changes. The mass has fallen far enough, the temperature has risen far enough, that the curve begins to bend in earnest. The evaporation quickens. Not suddenly, there is no sudden here. Not yet, but measurably, meaningfully, in a way that compounds on itself with the particular relentlessness of exponential change. Let that word sit for a moment. Exponential. In ordinary life, exponential growth is associated with speed, with things that double and redouble, that start small and become enormous in what feels like no time at all. But exponential change can also describe a process that starts enormous and becomes nothing. A decay. A curve that falls not linearly, not losing the same amount each unit of time, but proportionally, losing more as it has more to lose, losing less as it has less, until the losing itself becomes the dominant feature of the thing. That is what is happening to the black hole in the final stages of its evaporation. As mass decreases, temperature increases. As temperature increases, the rate of radiation increases. As the rate of radiation increases, the rate of mass loss increases, which increases the temperature further, which increases the radiation further, which accelerates the mass loss further still. It is a feedback loop. A slow one, at first so slow that calling it a loop feels misleading, feels too dynamic for something that unfolds over spans of time that contain more years than there are atoms in the observable universe. But as the mass falls and the temperature climbs and the radiation brightens, the loop tightens. The cycles shorten. The change that once took quadrillions of years to accumulate begins to accumulate in trillions, then billions, then millions. And the black hole, which has spent its entire existence as the embodiment of cold patience, begins for the first time to hurry. Breathe slowly. Let this next image form at its own pace behind your eyes. There is a moment, a conceptual moment, not a precise boundary, but a place on the curve where the character of the process shifts, where the black hole can no longer be described as cold, where its Hawking temperature has climbed, through the long accumulated weight of all that gradual evaporation, to something that would register as warmth, then as heat. The mass has fallen to the point where the inverse relationship between mass and temperature has begun to matter in a way that is visceral, rapid, undeniable. The black hole is now radiating at temperatures comparable to stars, then hotter than stars, then hotter than anything in the luminous era ever reached, except in the most extreme stellar deaths, the most violent supernovae. The radiation is no longer a faint trickle of low-energy particles indistinguishable from the background. It is a genuine, intense, blazing outpouring of energy, gamma rays, high-energy particles, radiation across every part of the spectrum, streaming outward from a black hole that is now very small, very hot, and losing mass at a rate that is, by the standards of everything that came before, catastrophic. The curve has become a cliff. There is something almost impossible to hold in the mind about this final stage, not because it is complicated, but because of what it represents. This black hole has existed for a googol years, or 10 to the 67 years, or whatever the precise figure is for this particular mass. It has drifted through the dark for a duration so vast that every attempt to picture it dissolves before it forms. It has been patient in a way that makes patience seem like an inadequate word, patient in a way that makes geological time seem hasty, that makes the entire history of the luminous universe seem like a moment. And now, at the end, it spends that last fraction of its total lifespan in a blaze. The final seconds, if seconds is still a meaningful word for what is happening, and in a sense it is, because events are now unfolding on timescales a human could, in principle, observe. The final seconds of a black hole's life involve the release of an extraordinary amount of energy. The last mass, the last remnant of what was once perhaps a stellar core or a concentration of primordial matter, converting to radiation in a burst that is violent and brief, and in the context of the long dark surrounding it, almost shocking. An object that spent a googol years being invisible radiates, in its final moments, with more intensity than anything nearby has seen in almost as long. Somewhere in the dark around you. Not close, never close in this dream, always at the safe distance of observation. One of these final moments is, in some corner of the universe, always happening, or will be happening, or was happening, in the time that the light from such an event would need to cross the distances of the dark era to reach any observer. Time and space have grown strange enough here that the grammar of before and after requires a certain gentleness, a willingness to hold it loosely. But somewhere, in the long story of the black hole era, a black hole reaches its final moments. And it does not end quietly. The last burst of Hawking radiation from an evaporating black hole is, in theoretical terms, explosive. Not explosive in the way of a bomb or a supernova. Not a pressure wave moving through a medium, not a shock wave expanding through gas and dust. There is no medium here, no gas, no dust. Just space, and the radiation itself, streaming outward in all directions at the speed of light. But intense. Genuinely, extraordinarily intense. A flash of gamma rays and high-energy particles, brief and brilliant, marking the place in space where something very old just stopped existing. And then nothing. A region of space that was for a googol years, the location of a black hole, is now simply a region of space. The mass that gathered there, from a stellar death, perhaps, or from the slow accumulation of a galaxy's worth of matter over billions of years of feeding, is gone, dispersed, converted entirely to radiation and carried outward at the speed of light, spreading and thinning into the vast dark. Nothing remains, not even a gravitational signature. The place where the black hole was is now, gravitationally, as empty as anywhere else. The curvature of space-time that made it what it was has smoothed away with the mass that caused it. The event horizon is gone, because there is no longer anything to create one. The particular configuration of space-time that constituted the black hole simply no longer exists. The stone in the river has dissolved. Let your body grow heavier as this settles. There is something unexpectedly moving in this arc. Something that speaks to things you know in waking life, about time and change and the relationship between long patience and brief endings. You have known, perhaps, people or things that endured for a very long time in stillness, in quiet, in a kind of suspended persistence, and then at some point changed quickly, released what they had been holding, completed something. There is no suffering in the black hole's final moments. There is no consciousness, no awareness, nothing that experiences the blaze. But there is something like completion, a curve that was always going to end this way, always bending toward this conclusion, finally arriving at the point toward which the entire googol years of patient existence was moving. The slow becomes fast. The cold becomes hot. The invisible becomes, briefly, the only thing that is happening anywhere nearby. And then it is over. And the dark is the same dark it always was, except emptier by exactly one black hole. One less island of structure in the expanding sea. One less remnant of the luminous era. One less monument to the mass that was once stars and gas and the bones of galaxies. The universe is a little lighter now, by an almost unmeasurable amount. But lighter. You are still floating. The dark is still the same dark. Your breath is still moving at its own quiet pace, independent of thought, independent of the vast timescales moving through you. The black holes around you are still in their long stillness. None of them is anywhere near its ending. The curve is still nearly flat, the temperature still nearly absolute zero, the radiation still invisible against the background warmth. They have a very long time yet, but the arc is there. The curve exists. The mathematics that describes the final blaze is the same mathematics that describes the current stillness. The same relationship between mass and temperature, the same inverse proportionality, the same feedback loop running so slowly it has not yet registered as a loop. It will register. Eventually. For now, it is enough to know that the stillness is not the whole story, that the patience has an end, that the long, cold, almost eternal dark of the black hole era is itself a passage between the luminous era that preceded it and the brief, final brightness that will conclude it, black hole by black hole, one last flash at a time. The slow death speeds up. The ending, when it comes bright. But it will not come for a very long time. And you do not need to wait for it. You only need to rest. You are very deep now. Deeper than you have been in a long time. Perhaps deeper than you have been in longer than you can remember. In the way that the deepest sleep is sometimes the least remembered, the most complete, the most total in its surrender. The passages that have come before have been doing their quiet work on you, layer by layer, the way water does its quiet work on stone. Not breaking anything, not forcing anything, just pressing gently and persistently until something softens, until something that was held begins, without drama, to release. You are released now, or nearly so, nearly all the way down. What comes to you in this passage is brief, shorter than what has come before, in keeping with its subject, because what this passage is about is the end of something, and endings, even very long endings, have a moment where they stop being gradual and simply become final. A moment where the curve that has been bending for a googol years arrives, at last, at its conclusion. This is that moment. Not your moment. You have a long time yet, and the night around you is warm and safe and unhurried. But the black hole's moment. The final passage of the last mass through the last stage of the longest process in the universe. Let it come quietly. You left the black hole in the last passage at the beginning of its final acceleration. The mass had fallen far enough, the temperature had risen far enough, that what was once the defining characteristic of this object, its cold, its patience, its invisible stillness, had begun to give way to something else. The feedback loop between temperature and mass loss, which had been running so slowly for so long that it might as well have not been running at all, had tightened. The evaporation had quickened. The curve that was once indistinguishable from a flat line had begun, unmistakably, to fall. Now you arrive at the bottom of that fall. In the final stages, the last phase of evaporation, when the mass has dwindled to something almost incomprehensibly small by the standards of what the black hole once was, the process does not slow down. It does not find a new equilibrium. It does not level off into some quieter mode of existence. It accelerates. The mass is small now. The temperature is high. And the relationship between them, that precise, unforgiving inverse proportionality that has governed every moment of the black hole's existence, is now working against whatever remains with a ferocity that the earlier stages gave no hint of. Every particle that escapes raises the temperature fractionally. Every rise in temperature increases the rate of emission fractionally. Every increase in emission rate decreases the mass fractionally faster. The fractions are no longer negligible. They are the whole story now. What once took quadrillions of years now takes billions. What once took billions takes millions. What once took millions takes thousands. The compression of timescales is dizzying, a lifespan measured in googol years collapsing, in the final chapter, into a sequence of durations that shrink so fast they pass through the familiar and into something almost instantaneous. Years become months. Months become days. Days become hours. The black hole is blazing now. Picture it, gently, from your safe and dreaming distance. What was for almost the entirety of its existence, the most invisible thing in the universe, has become the most radiant thing in its immediate vicinity. The Hawking radiation that spent a googol years as a whisper too faint for any instrument to hear is now a roar. High-energy photons pouring outward in every direction. Gamma rays, the most energetic form of light, streaming away at the speed of light. Particles of every kind that the energy budget allows, created and flung outward in the final extravagance of a process that was for so long the definition of frugality. The event horizon is shrinking visibly now. Visibly in the sense that the mathematics describes its retreat in real and rapidly changing terms, the radius pulling inward with each passing moment, the boundary of no return contracting as the mass it encloses diminishes. The black hole is quite literally getting smaller. Fast. faster than fast, by the standards of everything that preceded this moment. And the smaller it gets, the hotter it gets. And the hotter it gets, the faster it shrinks. The loop has become a spiral. The spiral has become a plunge. Let your breath come easily. Let the image simply be what it is. There is a temperature, a threshold, approached asymptotically, the mathematics climbing toward it the way a curve climbs toward a vertical line, beyond which the ordinary language of hot and cold becomes inadequate, beyond which the energies involved exceed anything that has existed in the universe since the first fractions of a second after the Big Bang. The final black hole, in its last moments, is not merely hot by the standards of stars or supernovae or even the early universe's ordinary epochs. It approaches conditions that existed only at the very beginning of everything. There is something extraordinary in that symmetry if you have the quietness to feel it. The black hole formed, whether from a stellar death or a primordial density fluctuation, in a universe that was already cooling from its initial extremity. It spent its existence in the long cooling dark, and at the very end it recreates, in the tiny volume of its final evaporation, temperatures and energy densities that the universe has not seen since its first moments. The end rhymes with the beginning. The last thing the black hole does is briefly become, in miniature, something like what everything once was. Hours become minutes. Minutes become seconds. The final seconds of a black hole's life are, in terms of energy release, the most intense moments the universe will experience in this entire long dark era. In a cosmos that has been, for incomprehensible spans of time, the definition of quiet. No stars, no supernovae, no collisions or explosions or any of the energetic events that filled the luminous age. This final burst is the loudest thing that happens. Not loud in the sense of sound. There is no medium here for sound to travel through, no air, no gas, nothing to carry a pressure wave. Loud in the sense of energy. Loud in the sense of radiation streaming outward with an intensity that, for a fraction of a second, outshines everything else in the observable universe, or what remains of the observable universe in this dark and attenuated age. The last fraction of mass converts. Not gradually anymore. Not in the slow, patient, particle-by-particle manner of the preceding Google years. In the final instant, the remaining mass, a tiny, hot, shrinking knot of curved spacetime, barely deserving the name black hole anymore, barely large enough to maintain an event horizon, gives up everything that remains. The event horizon reaches zero radius, and the black hole is gone. Gone completely. Not diminished, not transformed into something smaller, not leaving a remnant or a core or any lasting structure in the space it occupied. The mass that curved spacetime into a black hole has been entirely converted into radiation and carried away at the speed of light. The spacetime that was curved is no longer curved. The event horizon that was the defining boundary of this object's existence has ceased to exist because there is nothing left to create it. The location in space where a black hole existed for a Google years is now, simply, a location in space. Empty. Indistinguishable, gravitationally and physically, from any other empty location in the vast dark of the late universe. What remains is radiation. A sphere of it, expanding outward at the speed of light, carrying in its energy the last account of everything the black hole ever was. Whether that radiation carries, encoded in some recoverable form, the information about everything that ever fell into the black hole. Every star, every atom, every arrangement of matter that the black hole consumed over the entirety of its long life, is a question that physicists have argued over since Hawking first described the evaporation process. It is one of the deepest unsolved problems in theoretical physics. The information paradox, they call it. A question about whether the universe keeps records, whether the past is truly preserved in the present, whether what falls in must, in some sense, eventually come out. That question does not need an answer tonight. What matters tonight is simpler. What matters is the image, the expanding sphere of radiation, the last signature of something immense and patient and ancient, moving outward through the dark at the fastest speed anything can move, thinning and cooling as it travels, becoming, in time, indistinguishable from the background. A last breath, breathed out into the dark. Let yourself breathe out too. Not forcefully, just a slow, complete exhale, the kind that empties a little more than usual, that creates a moment of stillness at the bottom of the breath before the next inhale arrives on its own. Let that moment of stillness correspond, in some loose and undemanding way, to the moment after the burst. The moment when the radiation has left, and the space where the black hole was is simply space. The quiet after the ending is different from the quiet before it. Before the ending, the black hole's absence of light was the absence of something. The dark around it was a dark that contained something massive, something curving space, something that had gathered mass and held it, and would hold it for a googol years. The dark had weight in it, had presence, had the particular quality of a silence that is holding something back. After the ending, the dark is simply dark. No weight, no presence, no held breath. Just space, expanding at its own pace, carrying the last light of the last black hole outward in all directions until even that light is too thin to measure. Clean, complete. A kind of emptiness that is different in character from all the emptiness that preceded it. Not the emptiness of waiting, the emptiness of finished. There will be other endings. Each black hole in the universe will, in its own time, measured in its own particular googol of years, scaled to its own particular mass, arrive at this same conclusion. Some sooner, the lighter ones, the stellar remnants. Some much later, the supermassive giants, the ones that anchored the great galaxies and swallowed billions of stars over billions of years of feeding. But each of them will arrive. One by one, the islands of structure in the dark sea will complete their evaporation. One by one, the last bound objects in the universe will release their mass as radiation and cease to exist as objects. The universe will become, incrementally and irreversibly, a place with one fewer thing in it, until the last one goes. But that is for the next passage. That is the final chapter, the moment when the last black hole completes its journey, when the universe crosses a threshold it will never recross, when the black hole era ends not with a gradual fading, but with the last small burst of the last small fire. For now, here in the passage of the final explosion, let this one ending be enough. One black hole, one googol years, one last blaze, gone. The dark that remains is the same dark in which you are floating. The same deep, even edgeless dark that has held you through all of these passages, that has been your medium and your company and your bed. It has not changed. The ending of a black hole does not change the dark. The dark is too large, too established, too complete to be changed by the departure of any one thing, even a thing that was once the heaviest object in a galaxy. The dark simply continues. As you continue, breath by breath, depth by depth, settling further into the unhurried stillness that has been waiting for you underneath everything, underneath the day, underneath the thoughts, underneath the ordinary noise of being a person in a world full of light and sound and urgency. You are very deep now. The last explosion has happened somewhere in the dark, and the radiation from it is already traveling outward at the speed of light, already thinning, already cooling, already becoming part of the background. And the dark is 1 degree more empty than it was. And you are 1 degree more asleep. Let the next degree come on its own. It will. You are almost all the way down now. There is a place in sleep you have been there before, though you rarely remember it, where the boundary between the self and the surrounding dark becomes difficult to locate, where the body no longer feels like a distinct thing with edges and weight and position, but more like a quality of the dark itself, a slightly warmer region in something that has no temperature, a slightly denser presence in something that has no density, where the thoughts, if they come at all, arrive already half dissolved, trailing off before they find their endings, meaning less and less as they recede. You are near that place. Let this passage take you the rest of the way. What comes now is the quietest thing, yet quieter than the dark era, quieter than the cold patience of the black holes, quieter even than the long stillness between their evaporations. What comes now is the universe after its last structure. after its last object. After the final black hole has completed its Google-year journey and released the last of its mass as radiation and ceased, permanently and without remainder, to exist. This is what remains. Nothing happens quickly here. That is perhaps the first and most important thing to understand about the universe after the last black hole, that the transition is not marked by any event you could point to, any moment where everything changed. The last black hole goes the way all the others went, in a brief blaze that is extraordinary relative to the dark around it and negligible relative to the scale of what surrounds it. Its radiation expands outward. It thinning. It cools. It becomes indistinguishable from everything else. And then there is no everything else. There is only the background. The universe that remains is not empty in the way that a room is empty when the furniture has been removed, not empty in a way that implies the furniture existed recently and might return. It is empty in a more complete and final sense. Empty in a way that has no before to reference, no preceding fullness to mourn, because the fullness is so long ago that the word ago has lost its grip on meaning. Empty in a way that is simply the state of things, the permanent and universal condition of a cosmos that has finished doing everything it was ever going to do. What fills this emptiness, what constitutes the universe in this final era, is almost nothing. And almost nothing, spread across a space so vast that the word vast is no longer adequate, is for all meaningful purposes indistinguishable from its own name. Let your body be almost nothing for a moment. Not in a frightening way, not in the way of loss or dissolution or anything that asks something of you. In the way of relief. In the way that a body at rest is almost nothing, that the muscles have released their holding, the joints have found their ease, the breath has found its pace, and what remains is less the body as an active and effortful thing, and more the body as a warm and quiet presence, present without insisting on it, here without needing to announce itself. That is the texture of this era. Present without insisting. Here, but barely. What remains in the universe after the last black hole is, in the language of physics, a very dilute sea of radiation and particles. The radiation comes from everywhere and nowhere, in particular the accumulated output of every Hawking evaporation that has ever occurred, every stellar death, every energetic process from the luminous era, all of it long since redshifted and thinned by the continued expansion of space into wavelengths so long and energies so low that they carry almost no information and almost no capacity to do anything. This is not the warm, structured, meaningful radiation of a star, or even of the cosmic microwave background you know from the early universe. It is something far more diffuse, far more spent. It is the universe's exhaust, the last remnant of all the energy that was ever released by any process in the history of everything, and scattered through it, at distances so vast that the probability of any two of them ever interacting again approaches zero without quite reaching it, are particles. Electrons, positrons, photons, neutrinos, perhaps other things, hypothetical remnants of processes that occur on timescales even longer than black hole evaporation, the possible slow decay of protons into lighter particles, the quantum tunneling of matter into configurations of lower energy. The exact inventory of the universe at this stage depends on questions in physics that remain open, on decay rates and quantum processes that have not been measured and may never be. But whatever the precise contents, the character of this era is the same. Thin, cold, spread, inactive. The particles are so far apart that they will, in all likelihood, never meet. The radiation is so diffuse that it carries no usable energy, cannot drive any process, cannot power any change. The universe is not doing anything. Not because it is resting between activities, not because something is about to happen, but because there is nothing left that could happen. All the gradients have flattened. All the concentrations have dispersed. All the differences in energy and temperature and density that made things possible, that made stars and planets and chemistry and life and thought possible, have been smoothed away by the relentless tendency of energy to spread, to thin, to move from where it is concentrated to where it is not, until there is no longer a where it is concentrated and a where it is not. There is only where it is. Everywhere. Evenly. Thinly. This is what physicists call heat death. Not death in the sense of something dying. Nothing is dying here, because nothing is alive. Not heat in the sense of warmth. The universe is colder now than it has ever been, colder even than the long dark of the black hole era, cooled by the continued expansion of space to a temperature so close to absolute zero that the distinction is academic. Heat death is a technical term from thermodynamics, from the study of how energy moves and what it means for energy to be usable. Usable energy is energy that is unevenly distributed, energy that can flow from a place of higher concentration to a place of lower concentration, doing work in the process, the way water does work as it flows downhill. A star is usable energy, a vast reservoir of heat and light in a cold, dark universe, pouring its energy outward in a way that can warm planets, drive chemical reactions, sustain life. A temperature difference is usable energy. A pressure difference is usable energy. Any gradient, any unevenness, any place where things are not the same on both sides of a boundary. These are all forms of usable energy, all potential sources of the flow that makes things happen. Heat death is the end of gradients. The universe in this era has no gradients. The radiation is evenly distributed across space. The particles are too sparse and too isolated to create local concentrations of anything. The temperature is the same everywhere, which is to say it is as close to nothing as temperature can be. There is nowhere for energy to flow. There is nothing for energy to do. The universe is not violent, not turbulent, not active. It is not even peaceful in the way that a sleeping person is peaceful, where peace is the absence of disturbance in something that could be disturbed. It is peaceful in the way that a number is peaceful. It simply is what it is, without tension, without potential, without the capacity for change. Breathe in the evenness of that. There is something in this image that is not, despite its apparent bleakness, without a kind of beauty. Or perhaps beauty is not quite the right word. Perhaps the right word is something closer to completion. The universe has done everything it was going to do. Every star it was going to form has formed. Every element it was going to forge has been forged. Every planet that was going to cool and crack, and perhaps hold for a while the extraordinary accident of life has done so. Every black hole that was going to gather mass and hold it for a googol years and release it in a final blaze has done exactly that. And what remains is the sum total of all that doing, the final state of a system that started at one extreme and has arrived, over an almost unimaginable duration, at the other. The universe began in a state of enormous potential energy, enormous temperature, enormous density, a state from which almost anything was possible, from which complexity could emerge and arrange itself and build and burn and collapse and build again. And it has arrived, through the slow and patient operation of its own laws, at a state of minimum potential, minimum temperature, minimum density. It has arrived at the end of its own story. The first chapter and the last chapter of the universe are, in a certain light, mirrors of each other. At the beginning, everything in one place, all energy concentrated, no structure yet but infinite possibility. At the end, everything spread out, all energy diluted, no structure left and no possibility remaining. Both states are simple. Both states are, in their own way, featureless. What came between them, the long, luminous, complex, improbable middle, is the entire history of everything. You are the middle. You are always the middle. The particles that remain, drifting alone through the vast and lightless and nearly energyless expanse, are not nothing. They are something. Each electron, each photon, each neutrino is a genuine constituent of the universe, a real thing that exists and has properties and obeys the laws of physics. The universe after the last black hole is not nothing. But it is as close to nothing as a universe can be while still being something. And those particles, in their isolation, separated from each other by distances that make the distances between galaxies in the luminous era look intimate, are moving. Slowly, but moving. The universe is still expanding. Space is still stretching. The distances between particles are still growing, though growing slower now, or perhaps at some terminal rate, or perhaps in ways that depend on the dark energy that has driven the expansion since before the stellar era ended. This too is an open question, the ultimate fate of the expansion itself, and it does not need to be resolved tonight. What matters is the texture, the character. The particles drift, the radiation thins, the expansion continues or does not, or eventually reverses. But that too is so far beyond any timescale you have encountered in this dream that it is less a fact than a speculation, less a landscape than a rumor. Here, in the era you are floating through, the universe is in its final rest. Let yourself be in final rest too. Not the rest of ending. You are not ending, you are simply sleeping, simply drifting through this long and gentle night toward the morning that will come in its own time. But the rest of completion. The rest that comes after a very long day, after all the things that needed doing have been done or set aside or accepted as undoable, after the body and mind have traveled as far as they can travel and arrived somewhere quiet and horizontal and dark. That is where you are. The universe is in its heat death. It has arrived at the state from which there is no further transformation, no further doing, no further change that the laws of physics make possible. It is, in the most absolute sense, at rest. And you are floating in it, and the rest of it is your rest too, and the quiet of it is your quiet, and the vast evenness of all that dilute radiation and those lonely particles and that empty expanding space is, in this dream, indistinguishable from the quality of deep sleep, from the particular texture of a night that has given you everything it has to give and is now simply holding you, warmly and without agenda, while the hours pass. There is no clock here. There is no morning pressing at the edge of things. There is only the dark and the faint warmth of the last radiation, and the particles moving too slowly and too far apart to ever trouble anything, and the silence that is not the silence of waiting but the silence of arrived. The last black hole is gone. Somewhere behind you in the long dream of this night, it completed its journey. The curve arrived at its conclusion. The blaze happened and faded, and the space where it happened smoothed back into evenness. And this is what came after. This thin, cold, even patient, permanent almost nothing. This universe that has used itself up completely, spent every gradient, dissolved every structure, dispersed every concentration of energy into the background from which nothing more can be made. This is the end. Not an ending you need to fear. Not an ending that takes anything from you. You are here, warm, breathing, held by the planet that made you, in a universe that is still, by the standards of what you have been drifting through tonight, blazingly young. Not an ending that asks anything of you. Just an ending. The universe's own long exhale, drawn out over timescales that make the word long meaningless, finally, finally, finally complete. Let your own breath follow it. Out. Slowly. All the way. And then let the next one come on its own. It will. It always does. You are almost gone. Not gone in any final sense. Gone in the way that sleep takes you, in the way that the deepest rest dissolves the edges of the self until what remains is less a person with a name and a history and a list of things to do tomorrow, and more a warm, quiet, breathing presence in the dark. The thoughts that have been moving through you tonight, the vast timescales, the fading stars, the patient black holes, the final blaze, the thin and even dark of the universe's last era, have done their work. They have carried you somewhere. Somewhere below the surface of ordinary consciousness, somewhere in the deep and undisturbed water beneath the chop of daily life. This is the last passage. It will not be the loudest. It will not bring anything dramatic. No new explosions, no new mechanisms, no new mathematics to let wash over you. What it brings is something quieter than all of that. Something that is, in its own way, the most restful thing of all. It brings uncertainty. Not the frightening kind. Not the uncertainty of not knowing whether you are safe, or whether things will be all right, or whether the future holds something you should be worried about. The other kind. The kind that belongs to science at its most honest, to human knowledge at its most careful edge, to the place where what is known gives way to what is genuinely, openly, beautifully unknown. The universe, it turns out, has not finished surprising anyone. And that is where this long night ends. Everything you have received in the passages before this one, the fading of stars, the black hole era, the timescales measured in googolls, the mechanism of Hawking radiation, the final evaporation, the heat death, all of it is real. Real in the sense that it follows, with mathematical precision and deep internal consistency, from the best physical theories humanity has constructed. Real in the sense that physicists who have examined these ideas carefully, who have tested the underlying frameworks against every observation available, find them not merely plausible but compelling. Real in the sense that the universe, as best as anyone can determine, actually works this way. But there is a distinction worth holding, here at the end of the night, between what is mathematically derived and what is directly observed, between what the equations say and what any instrument has ever measured. No black hole has ever been observed to evaporate. Not partially, not completely, not at all, in any directly detectable way. Hawking radiation remains, as of everything that is known, a theoretical prediction, one of the most beautiful and well-supported theoretical predictions in the history of physics, one that connects frameworks of stunning depth and power in a way that almost no physicist who has studied it seriously doubts. But a prediction nonetheless. The universe has not yet confirmed it through the direct testimony of observation. Let that sit without anxiety. It is not a crack in the foundation. It is the nature of knowledge at its frontier, where the theories are running ahead of the instruments, where the mathematics is describing processes too faint, too slow, too remote in time to be caught by any eye or detector. Science has always had this quality at its edges. The best ideas have always lived, for some period, in the space between theoretical confidence and experimental proof. Hawking radiation is in that space. It is, by almost every measure of theoretical physics, almost certainly real. Almost certainly. And that small remainder, that honest, careful, scientifically appropriate almost, is what makes the universe still interesting. Breathe slowly. The questions that remain open are not small ones. The deepest of them is the question of quantum gravity, the reconciliation of general relativity and quantum mechanics that physics has been reaching toward for nearly a century without fully arriving. Hawking's discovery was a window into that reconciliation, a glimpse of what a complete theory of quantum gravity would need to contain. But it was not the theory itself. The full theory, the framework that would describe, without approximation or ambiguity, what happens to space-time and matter when both quantum effects and gravitational effects are simultaneously important, does not yet exist. And the end state of black hole evaporation is precisely the kind of situation where that full theory would matter. In the final moments of evaporation, when the black hole's mass has dwindled to something approaching the Planck mass, the fundamental quantum unit where gravity and quantum mechanics become inseparable, Hawking's calculation begins to lose its footing. The approximations on which it rests, the assumptions that make the mathematics tractable, are no longer reliable at that scale. What actually happens in the very last instant, as the last remnant of mass converts to radiation, is something that the current theories cannot fully describe. Does the black hole evaporate completely, leaving truly nothing behind? Does it leave some kind of stable remnant, a tiny inert object at the Planck scale, a permanent relic of the event horizon that once surrounded it? Does the information that fell into it over a googol years somehow emerge, encoded in the final burst of radiation in a form so subtle it requires a complete theory of quantum gravity to read? Does something else happen entirely, something that nobody has yet imagined, because the theory that would suggest it has not yet been written? These are not rhetorical questions. They are genuine open problems, actively worked on, genuinely unresolved, at the frontier of human understanding of the universe. There is something unexpectedly comforting in this, if you let yourself feel it. You are a creature of the middle of the universe's story. You live in the luminous era, in the 10 billion year window when stars burn and planets cool, and the conditions for complexity and life and thought exist. And you are also a creature at the middle of human knowledge, living in the period when the theories have grown extraordinary in their reach and precision, when the instruments have become capable of things that would have seemed miraculous a century ago, and yet when the deepest questions about the nature of space-time and the final fate of matter remain genuinely open. You are not at the end of understanding. No one is. The universe has not finished teaching. And there is rest in that, a different kind of rest than the rest of completion, the rest of arrived. This is the rest of not needing to know, of being comfortable at the edge of the known, of letting the open questions be open without experiencing them as threats, of understanding that the universe's mysteries are not problems to be solved before sleep, but companions to be carried lightly, gifts from a cosmos that is more interesting than any final answer could make it. There are other mysteries waiting at the edges of what this night has described. Some recent thinking in theoretical physics suggests that the story of slow evaporation over immense timescales may not belong exclusively to black holes. Other very compact objects, neutron stars for instance, or other dense remnants of the stellar era, may also, through quantum processes operating on timescales that rival or even exceed those of black hole evaporation, slowly lose mass, slowly change, slowly participate in the long unwinding of the universe in ways that classical physics would not have predicted. The details of these processes are uncertain, and the timescales involved are in some cases even longer than what you have already encountered tonight. Timescales that require new notation, new ways of writing numbers, new conceptual frameworks for what it means for a process to take as long as it takes. Whether these processes are real, whether they operate in the way the theoretical calculations suggest, whether they change the inventory of the universe's final era in any significant way. These are questions that live at the furthest frontier, where the mathematics is still being worked out and the physical intuition is still being developed. New physics could change everything. Not in the sense of overthrowing what is known. The great theories of the 20th century have proven too precise, too experimentally verified, too deeply woven into the fabric of how everything works to be simply wrong. But in the sense of extending what is known, adding new layers to the picture, revealing that the universe's final chapters are stranger, longer, more intricate than any current model fully captures. It has always done this. Every era of physics has discovered that the universe is more surprising than the previous era suspected. There is no reason to believe this process has ended. Let your mind grow soft around these open questions. You do not need to solve them. You were not given tonight to solve them. You were given tonight to rest in them, to let the vastness of what is known and the vastness of what is not known exist together in the dark, two kinds of immensity lying side by side, neither one diminishing the other. The universe is 14 billion years old and will last at least a googol more. Everything known about it was discovered in a period of a few centuries by creatures who live for less than 100 years on a small rocky planet orbiting an ordinary star in one of hundreds of billions of galaxies. And in that brief, improbable window of discovery, those creatures found Hawking radiation and thermodynamics and quantum field theory and general relativity and the cosmic microwave background and the expansion of space and dark energy and the long arc of stellar evolution from hydrogen cloud to iron star to black dwarf to cold remnant. They found the shape of the universe's story. Not all of it. Not the ending, not quite. Not the very last chapter, not with certainty. But the shape. The broad and extraordinary sweep of it, from the first fraction of a second to the heat death, from the smallest quantum fluctuation to the largest supercluster, from the particle to the cosmos. You are one of those creatures. You carry that knowledge with you, even in sleep. Even here, in the deep dark of this long and quiet night, the knowledge is part of you, not held as data, not accessed as information, but present the way that deep things are present, the way that everything you have ever learned is present, threaded through the structure of how you see and feel and move through the world. You have looked at the universe tonight and seen something true about it. That it is vast beyond comprehension, and that comprehension reaches for it anyway, and that the reaching is one of the most beautiful things that happens in the luminous era. That the black holes are real, and the evaporation is real, and the long dark is real, and the heat death is real, and the questions that remain open are real, and the wonder that attends all of it is real. All of it is real. The last black hole is somewhere in your future. So far in your future that the word future barely applies, that future and past and present have all dissolved into the single enormous fact of time, time continuing, time accommodating everything that will ever happen the way the dark accommodates everything that drifts through it. You do not need to go there tonight. You are here. In the warm, in the breathing, in the body that is heavier than it was when this night began, in the mind that has traveled very far and is now, at last, content to be still. The universe will take care of its own ending. It has the tools for it, the quantum fluctuations at event horizons, the slow radiation, the long timescales, the final blaze, the thin and even dark that follows. It does not need your attention to proceed. It will proceed without you, and without anyone, and it will proceed correctly, in accordance with laws that are true whether or not anyone is there to observe them. You are free. Free from the need to understand, tonight. Free from the need to hold any of this precisely. Free to let it dissolve from the foreground of awareness into the background, from the surface into the depths, from the light into the dark, where everything that has passed through your mind tonight will rest and settle and become, quietly and without effort, part of the texture of how you know the universe. Sleep now. The black holes are patient. The timescales are long. The questions are open. The universe is continuing its slow and extraordinary work in the dark, particle by particle, moment by moment, without urgency and without end, or with an end so far away that it is, for all purposes that matter to you tonight, indistinguishable from forever. Let forever hold you. Let the dark be what it has been all night, not empty but full. Full of distance, full of time, full of the quiet persistence of things that last. Full of the radiation that was once a star, and the star that was once a cloud, and the cloud that was once the early universe, and the early universe that was once a point of infinite potential from which everything emerged. You emerged from it too. You are part of the same story as the black holes, and the fading stars, and the long dark, and the final mystery. Made of the same atoms forged in the same stellar furnaces, governed by the same laws, subject to the same deep grammar of a universe that is, in its own vast and patient and finally unknowable way, astonishing. It is astonishing. You are astonishing, and you are at last asleep.